In this video, I wanted to discuss the motorcycle example from our physics notes this week. We have a motorcyclist that's trying to jump a canyon, as shown in the diagram here. The motorcyclist is traveling with an initial velocity of 38.0 meters per second. And if we ignore air resistance, we'd like to find the speed with which the motorcycle hits the ground upon landing. Now we're completing this particular question while we're studying the work and energy. So there's a work energy theorem that would work for this. But also let's just remind ourselves that our old kinematics equations could work too. So if we recall in a problem like this, we might recognize that initially when this motorcycle leaves the cliff, they have an initial velocity in the x direction and an initial velocity in the y direction. Now, because we're looking right at the beginning of this event, this person or this rider doesn't have any initial velocity. In the y direction, it's equal to 0, so we only have this forward-facing vector. But as this rider continues to careen through the air, they also have they have velocity in the x direction in each of these points along the way. And what's important to note is at the point of impact, they also have a velocity in the x direction right at the point of impact. I'm going to call this one the final velocity in the x direction. And because we're ignoring air resistance, the velocity in the x direction remains unchanged. There is no force affecting the velocity in the x direction. Vertically, on the other hand, since we're here on Earth, I assume that we're on Earth, we're experiencing gravitational acceleration, and the velocity in the y direction continues to increase as we travel forward. So while our initial velocity in the y direction was 0, the velocity in the y direction for the remaining instances is starting to increase. And when we're finished here, we'll have some sort of final velocity in the y direction. Now, as I understand it, this particular question is not interested in the speed in any one direction, but we're really interested in the speed altogether. So we want to know the final speed of this motorcycle, and that's taking into account the horizontal speed and vertical speed together. So before we use our work energy theorems to address this, let's go ahead and try to answer this using kinematics from a prior unit in this class. I would note that our initial velocity in the x direction is going to be our 38 meters per second. I would note that our final velocity in the x direction is also 38 meters per second. That remains unchanged in our projectile motion. We have an initial velocity in the y direction of 0 meters per second. The final velocity in the y direction, that's unknown. But I think we can figure that out because we do know that the acceleration in the y direction is the acceleration due to gravity, and that's negative 9.81 meters per second squared. Notice I'm using negative 9.81 to indicate direction of travel here. I'm not using just plain g, I'm using acceleration due to gravity, ag, or better still, I can generically call it ay. The y position initially was 70 meters above the ground, or above some starting point. And our y final position is 35 meters above some measured point. So these two together tell me that delta y is equal to negative 35.0 meters. We know that because we should take our final quantity and subtract our initial quantity. That produces negative 35 meters. And then also back to here, one of our kinematics equations indicates that our final velocity squared is equal to initial velocity squared plus 2 times our acceleration times our displacement. So in this case, change in y, because we're worried about the y direction. So that formula is going to be helpful for us. So I'm also going to note that our final velocity, or the magnitude of our final velocity, I should say, down this diagonal And to be careful, I will put the magnitude bars here. The magnitude of our final velocity is equal to the square root of the magnitude of our velocity in the x direction. And I'm going to note that that's the final velocity in the x direction squared, plus the final velocity in the y direction squared. So the final velocity in the x direction, we know that already. We know that to be a quantity. So we'll square that. The final velocity in the y direction, well, I'm going to use this rule over here for a second. The final velocity would be the square root of this expression on the right side. So we have the square root of v naught in the y direction, v naught in the y direction squared, plus 2 times acceleration in the y direction times the change in y. So that quantity would then need to be squared, but we know that the square and a square root are inverses of each other, so they'll cancel each other out. So here's a good expression, and I think we have all the components that we need. And if we substitute our known quantities for the initial velocity in the x direction and the y direction, as well as our acceleration in y and the displacement in y, we see a setup that looks like this. And according to the calculator that I have off screen, it's showing a 46.1595 result. Now I hope that this is meters per second, but we really should do our dimensional analysis to check. So our velocity unit squared, meters per second quantity squared, that occurs twice because of our velocity in the x and the y directions. And then after that, we'll add to it a scalar that multiplies by a meter per second squared and a meter. So all three of these would then be alike one another. These two combine to make a meter squared over second squared, while these combine to make a meter squared over second squared. All three terms can sum together and produce a meters squared per second squared. And then when we come by and complete the final algebraic manipulation of taking a square root, that does indeed leave us with a unit, meters per second. So this appears to be a good answer. And if we consider our significant figures, it looks like all figures were reported to 3 decimals, and reporting an answer of 46.2 meters per second seems reasonable. That's fine. That's great. So this is how we could complete this problem using kinematics, our equations from Unit 1 and Unit 2. But what if we were to use the new stuff? What if we were to use the work and energy theorem that we have from Unit 3? Well, the work energy theorem in Unit 3 indicates that our energy amount total at the end of the event should be equal to the energy amount total at the beginning of the event. It's our conservation of energy. And for us, we're discussing our kinetic energies and potential energies. So the kinetic energy and potential energy are what combine to make our total energy in this case. And so the sum total of the energies in the final position would be equal to the sum total of the energies in the initial position. So if we were able to compute the kinetic energy of the motorcycle rider at the beginning of the jump and at the end of the jump for both, kinetic and potential, then sum those together and they would be equal at the beginning and the end of the event. Now, kinetic energy we've described as 1/2 of the rider's mass times their velocity squared. And since we're talking about final kinetic energy, we'll use VF squared. The potential energy is mass times gravity times height, so the height at the final position. And this, again, is gravitational potential energy. We don't have like spring potential energy or anything like that. We're going to use 1/2 mass velocity squared for our kinetic energy at the beginning. We'll use a subscript of 0 to indicate that. And similarly, mgh subscript 0 for our initial potential energy due to gravity. Now, our goal is to find the final velocity of the motorcycle and rider combo. And back here, we had to worry about the horizontal and vertical components that went together to make this diagonal velocity. But that's precisely what our formula here is actually allowing us to compute. Let's see if I can slide this thing back over. That's precisely what our formula here is actually computing. We don't have to worry about this diagonal measurement. It's already representing the diagonal. This is the essentially tangential or straight line velocity, even though we're facing downward and at an angle here. So if we start thinking about what's necessary to isolate our final velocity, there might be some additional steps to show along the way, but I'm going to show this one at least at first. I like leaving these terms alone here, and I'm going to bring everything else over to the right side. So that means subtracting this group to the right side, dividing or multiplying to remove the 1/2, dividing the m value over, and then using a square root to remove the exponent of 2. So that would look something like this. Half of our mv initial squared plus mgh initial. We'll subtract from that the mgh final. Divide that by 1/2, which would be the same as multiplying by 2. So I'll just multiply that by 2. That takes care of this. This is already gone. We divide everything by m. That takes care of this. And then place all of that underneath a radical sign. So there's an expression. We can actually fill in our quantities here and proceed if we'd like, but it's also worth noting that we can simplify just a little bit. This 2 on the exterior of the parenthesis group here can be distributed 3 different times. So the 2 and the 1/2 is going to cancel. It's going to create a 2 coefficient here and here. And now you might notice that we have a 2mg that's a common factor amongst those two terms. But also while we're here, we'll note that the m quantity in the denominator of this fraction can factor the m quantity from each of these terms, separated by an addition and subtraction sign, from the numerator of the fraction. So now actually m is all the way gone. And so while this 2 and this 1/2 canceled and the 2 got distributed into these new positions, we actually see an expression that looks something more like this. We have our initial velocity squared plus 2 times g times h naught minus 2 times g times hf, and all of that underneath a square root. And if we take notice one more time, simplifying this expression, v naught squared plus 2g times h naught minus hf. Well, would you look at that? This looks an awful lot like the expression that we landed on back here, where we had an initial velocity squared plus, well, I guess this already disappeared, plus 2 times an acceleration times a change in y. And so here we have the same thing, initial velocity, 2 times an acceleration, and multiply by a change in y. So the formulas end up becoming remarkably similar to one another. In fact, one could argue that they're exactly the same, especially when you account for this notion of delta y, in this case reporting as a negative number, but that negative multiplied by our acceleration, which is negative, turns positive. G we always report as a positive number. And in a case where we have an object that's falling due to gravity, h naught minus hf would actually always be reported as a positive number, because our initial position would be higher than our final position. So we'd get a positive result here. So they're essentially the same. Now when we substitute these quantities into the calculator, our 38 squared plus 2 times 9.81 times 70 minus 35. The computer result does come out to be the exact same. We get 46.1595 meters per second. And with sig figs, we can call that 46.2 meters per second. Our dimensional analysis should support this, and it does. So at this point, before we substituted in quantities, we had a meter per second that got to be squared. That unit was squared. Then we had an acceleration unit, meter per second squared, and a displacement unit of meters. So we have a meters squared per second squared after these are multiplied and combined. And of course, the square root, which is necessary to this computation of that expression, does yield the dimensions that we're after. So while this first group of math leads us to the solution using kinematics, this series of computations leads us there by using our work-energy theorem. And it's nice to note that we can tell that the velocity in either case computes to be exactly the same. So I hope that helps clarify some things, especially if I went too fast in class today. You can pause and replay as necessary to check your work. Thanks for watching.